welcome to this video. We're going to be talking about strategies for testing infinite series. Alright, so this video is targeted for the students at UCI Math 2B, but if you're taking like AP Calc BC or some equivalent course, this might be helpful for you also. Okay, so most people have a hard time with this because they're not very comfortable with infinite series, and two, it's near the end of the course, it's the newest topics, they haven't got a lot of time to practice it. So I'm just here to tell you the strategies that I use and that are usually good enough to help you get the problems correct, or at least get most of the points on the UCI Math 2B final, okay? So let's go down this list of things that I wrote. So there's some things common patterns that I look for, and then there's some things that you just need to know. Okay, for example, the very first point, you should be able to recognize special series, namely the P series and the geometric series. Right? We know that P series is convergent when P is greater than 1, is divergent when P is less than 1. Geometric series, the absolute value of the common ratio has to be less than 1 for it to converge. Others are diverges, okay? You got to know those. We can always use the test for divergence first. You can just, you don't have to even write it down and all that. You can quickly look at the limit and see if the limit goes to 0 or not. If it does not go to 0, then it's divergent. If it does go to 0, then we have to try some other thing, all right? For ones that deal with the integral test, a lot of the times, for the problem, writing the problem's sake, there's usually a very obvious substitution that you can make. All right, so if there's an obvious U substitution, we can try the integral test. Of course, for the integral test, there are conditions that need to be met. The function needs to be positive and decreasing, or the infinite series needs to be positive and decreasing. So you can check that with the equivalent function or corresponding function. They're not equivalent. The corresponding function in continuous time, continuous domain instead of discrete. Okay. If there's a -1 to the n or equivalent, like a changing sign type of thing, a good candidate to use is the alternating series test. If there's an exponential or a factorial, a good candidate is the ratio test. If the whole series is to the n power, a good candidate is the root test. And then the very last resort is the comparison and limit comparison test. This is it's kind of the thought process that I go through. All right, I try to save these for last because these sometimes are a little more involved in picking a series to compare with. These are more straightforward algorithmically, all right? So that's why I put this last, okay? So we're gonna use this reference sheet to solve some problems now, okay? By the way, I have made this video before on my old channels, and it was very popular actually amongst people that I personally know and people that watched it who came across the video. Okay, so these are the same problems, and some are very typical. You can expect like the same level of difficulty on the Math 2B final. Some are a little more difficult. So if you are able to get all these problems, then you're in very good shape. All right, so let me get that over. Okay. So in my old video, I did not even solve all of them. I just said which test that I would use. So here I actually pre-solved all of them. All right, so we have this infinite series from 1 to infinity, 1 plus sine n over 10 to the n. Okay, so we go down a list. I don't see that it's a special series. Well, 1 over 10 to the n is a geometric series, but sine n over 10 to the n, it's alternating sine geometric series. Oh, actually, no, it doesn't even alternate sine because of sine n. It will change signs on some terms, but it won't change sign for every other term. I mean, every term. So it's not like plus, minus. It might be like plus, minus, minus, plus something like, I don't know what it is, but it's not always changing signs. So it's not an alternating series for sure. But anyway, so I don't recognize as any of the special series that you learn. Test for divergence. Well, clearly it goes to 0 as we take the limit as n goes to infinity because this exponent will dominate over what 1 plus sine n, whatever that can do. Sine n is just between -1 and 1. So this at most could be 2. So the exponent will make the sequence go to 0. So that's fine. I don't see an obvious U sub. I just went over this. It's not alternating series. This is not a ratio test probably because of the sine n. That'll be hard to cancel out terms. This whole series is not to the n power, so not the root test. So we're at our last resort. Comparison or limit comparison test. Okay, so what can we compare this series with? So I mentioned earlier that sine n is between -1 and 1. Right? That's how the sine function looks. So we can use that to our advantage, okay? Since sine n is between -1 and 1, 1 plus sine n over 10 to n, that's the sequence, is less than or equal to 2 over 10 to n. So as I said earlier, sine n, the maximum value it can take ever is 1. So it'll be the maximum value that the top can be is 2. All right? So 2 over 10 to the n is greater than or equal to our sequence, okay? And this guy we know the convergence of because it's a geometric series. We can rewrite it as, so this is the series. We can move the 2 outside and we can rewrite it as 1 over 10 to n power. This is convergent because it's a geometric series with the common ratio of 1/10, which is less than 1. Okay, so since this guy converges and our original guy is smaller than this guy, then our original guy must also converge by the comparison test. Okay? So that's how we can solve this one. This one is a little more challenging, I would say. It's like more intermediate than fundamental, okay? But it's a good level to try. Hi, this is more of a fundamental one, all right? We have this summation as n goes from 1 to infinity, n squared over n cubed plus 1. Okay? I don't see it's a special series. Test for divergence, clearly it goes to 0 as n goes to infinity because the denominator degree is bigger. Is there obvious U sub? It's doable if we let u be n cubed plus 1. So we can keep that in our the back of our mind for now. It might be usable. -1 to the n or equivalent. It's not alternating series, so no. Is there exponent or factorial? I don't see one, so not this. The whole series to the power of n? No. Or can we use a comparison or limit comparison test? So either the integral test or comparison or limit comparison. So I personally did not choose to use the integral test. Instead, this I can compare with a p-series. This is a very typical compare with a p-series type of problem. So I used actually the limit comparison test here. All right, so the technique here is when it looks like, if it's a function, it's like a rational function. But this is a series, but I'm just going to use the term rational function. When we see something like that looks like a rational function like this, we can easily, most of the time, we can easily compare it with the biggest degrees, okay? So I picked the biggest degree on the top, which is just n squared. The biggest degree on the bottom is n cubed. If there's a coefficient out in front, we can keep it also, all right? So this can simplify to 1 over n. This guy, we know diverges. This is the harmonic series. So let's try the limit comparison test. Limit as n goes to infinity of this guy over this guy. So that's why I wrote over there. We simplify. Limit as n goes to infinity. This 1 over n, we can move to the top, n cubed of n cubed plus 1. This limit is equal to 1. What does the limit comparison test say? The limit has to be finite and greater than 0, which it is. All right? So, since this guy diverges, this guy must also diverge. That's what the limit comparison test says. All right? So that's how I solved this one. Okay. Next, we have this. So you already see that I did an integral test probably, but that's okay. We have this series. Okay, so here I see an obvious substitution that could be made if this were an integral like this. All right, so that's why I decided let's try the integral test. Okay, so for the integral test, we have to show that the series or the corresponding function, is positive and decreasing. So if I say f of x is 1 over x squared ln x, so I just put this as a function instead, we know this is positive for x is greater than or equal to 1. Why this x greater than or equal to 1? Well, the infinite series starts at 1, okay? How do we know it's positive? Well, x will be positive, log x will be positive as well, okay? And actually, I should write it as x greater than 1, or we can say x is greater than 2, all right? Remember, for the integral test, as long as it is positive and decreasing from a finite number and all the way to infinity, that's fine. It's just a finite number of terms before that we can simply add, okay? Hopefully that makes sense. If not, you can probably review your notes about the integral test. I'm sure your instructor should have mentioned that, okay? So let's find f prime to figure out that this guy is decreasing. We found it's positive. Does it decrease? Well, okay, so this is the differentiation. So I won't go over that. You would need the let me briefly go over it. This guy I rewrote in my head as x squared ln x all to the -1 power. So I first did the power rule, so that's here, and then chain rule, so derivative of the inside, which I needed product rule. And then this line I simplified. Okay, so you can pause the video and look over that yourself. Okay, and we see that f prime is less than 0 for x is greater than 2. Okay, so how do I know that? Well, again, log x is always positive, all right? And then this guy squared is always positive, okay? Remember, for x greater than 2, this is my condition. But then there's this negative sign out in front, so it'll make the whole thing negative, okay? So f prime is negative for x is greater than 2. So I said this sequence is positive and decreasing, all right? So we have to say these in order to use the integral test. I don't know how UCI grades this, honestly, but you should at least state this, bare minimum, even if you don't show work. All right? All right, so we find the integral from 1 to infinity, 1 over x squared ln x dx, okay? We let u be ln x, du is 1 over x dx. So we make the substitution, all right? And then we had to change the limits of integration also. So I didn't do it the limits way, so I did it the quicker way that most people actually do. So when x is 1, u is ln 1, which is 0. When x approaches infinity, u also approaches infinity, because ln x, as x goes to infinity, approaches infinity. So the limits are 0 to infinity, 1 over root u du. This is simple power rule, 2 root u from 0 to infinity. So we get infinity. So the series diverges by the integral test. All right, that's how I solved this one. Once again, I saw there was a clear substitution that could be made. So integral test was the good candidate. All right, this is a typical type of problem that you can expect in the final. Okay. You already probably saw it, but that's okay again. How about here? We have this series n squared e to minus n. Okay, so I'm not going to just go through all the list again. You can go through it slowly yourself. But here I see there's an exponent. So which one is that? Ratio test. That's a good candidate. So I used the ratio test here. Limit as n goes to infinity, if this is a sub n, it's a sub n plus 1 divided by a sub n. So this is what I did over here. All right, n squared plus 1, I expanded out here, though I didn't need to. N squared I left alone. E to the negative n plus 1 over here is actually e to the negative n minus 1, okay? So when we divide that by e to the negative n, we're left with e to the negative 1. Okay, that's simple algebra there. All right, so as the limit goes to, as n goes to infinity, e to the negative 1 is a constant, so we can technically pull it out. Okay, so let me even circle that, pull that out. What happens as n goes to infinity of this guy? Well, remember, same degree, take the ratio of the leading coefficients. So that's 1, but we're left with this e to negative 1 still, okay? Remember, e is about 2.7, so this guy is approximately 1 over 2.7. We know 1 over 2 is 0.5. 1 over 3 is 0.33 repeating, right? So it's for sure a number less than 1. So this guy converges by the ratio test. Next we have this one. Summation n goes from 1 to infinity, 1 over n cubed plus 1 over 3 to n. This you should recognize is special series. Okay? One of them is a p-series, one of them is a geometric series. Okay? So I first broke it up into summation as n goes from 1 to infinity, 1 over n cubed plus summation of 1 over 3 to the n. So this we know is a p-series with p equals 3, so that converges. This guy is a geometric series with r is 1/3, which is less than 1. That converges also. By the way, p is greater than 1 here, so it converges. So we know this converges. Okay? Since we know these two special series. All right. Next, we have a factorial. Which one's that on the list? Ratio test. All right? So I'm going to take the limit at the end, but I'm going to do the a sub n plus 1 over a sub n over here. Right? So this is it. All right, so we simplify 2 to n plus 1 divided by 2 to n. We're left with 2 on top, so that's here. N plus 1 factorial divided by n factorial. Remember, n plus 1 factorial is n plus 1 times n factorial. So we're left with n plus 1. Now over here, remember n plus 3 factorial is n plus 3 times n plus 2 factorial, so we're left with n plus 3. Okay, so now we take the limit as n goes to infinity of this guy. Okay, once again, we technically can pull the 2 outside in front, all right? So we're left with n plus 1 over n plus 3. Once again, we just take the ratio of the leading coefficients. That's 1, so 2 times 1 is 2, right? This is greater than 1. So what does the ratio test say? This says it's divergent. Okay. This one's pretty standard for the Math 2B final, I would say. Okay, now this one is a little trickier. Okay, it's more involved, so if you can get this one, that's good. We have summation as n goes from 1 to infinity, 1 over n to the 1 plus 1 over n, okay? So here, let's go down a list, okay? It's not a special series. How about test for divergence? As n goes to infinity, what do we get? We get infinity on the bottom, so it goes to 0, so that passes, so we don't know if it actually diverges. Is there obvious substitution? I don't see it, so maybe not that. Definitely not alternating series. I don't see a negative 1 to the n. Ratio and root test. Well, I don't see, it's the whole thing to n power, so not the root test. How about ratio test? I don't see like a factorial or exponent, so probably not that. So are we at our last resort comparison or limit comparison test? So I just chose to, first of all, rewrite this as summation as n goes from 1 to infinity, n times n to the 1 over n power. We can break this exponent up into this, all right? Because it's n to the 1 times n to the 1 over n power. All right, so why did I want to write like this? Well, I'm thinking, well, what if I do a limit comparison test with the harmonic series 1 over n? Okay, because I thought that because mathematically, when we do a limit comparison test, we would divide these two and the 1 over n's would cancel. That's what I was thinking. Okay, so we take the limit as n goes to infinity of what I just said, the ratio of the two sequences. All right, so the 1 over n's cancel as I just said, so we are left with 1 over n to the 1 over n. Okay, which we can rewrite as limit as n goes to infinity of n to the minus 1 over n power. All right, so here, how do I get the limit is 1? Well, here, remember, we have to use L'Hopital's rule, but L'Hopital's rule is 0 over 0 and infinity over infinity, so we have to get it to a quotient form. And we do that by, so here I just said, let y be x to the minus 1 over x. So instead of n, I put x, and I said that equals y. All right, so log y is log of this guy. I just ln both sides, right? And by properties of logs, I can move the exponent out in front of the log. So it's minus 1 over x times ln x. Right? So now I take the limit as x goes to infinity of this guy, which I can write as minus log x over x. So here I can use L'Hopital's rule now because as x goes to infinity, we get infinity over infinity. So we can use L'Hopital's rule. Limit as x goes to infinity of derivative of log is 1 over x, is that negative sign still, divide by derivative of x is 1. So this is 0. All right? Notice we found the limit of log y. So hopefully this sounds familiar. We want y though, so we have to exponentiate it. So limit as x goes to infinity of the original y, which is this, is e to the 0, which equals to 1. Okay, so that's how I found out this was 1. Okay, remember we're doing the limit comparison test, so this is why this is a little more involved and more advanced. What does the limit comparison test say? Since this limit is greater than 0 and finite, because this guy diverges, this guy also diverges, right? So that's what I wrote here. All right, so hopefully this one was helpful to try. This is definitely a more difficult one. I don't think they'll really ask this level on the UCI Math 2B final, but if you can do this, you're in very good shape. All right. Okay, next we have this one. There's an alternating sign, so immediately I think let's try alternating series. All right, there's conditions for alternating series. Remember, the sequence without the alternating sign has to be decreasing. Is it? It is, okay? That should be clear, so I feel like you could just write this and it's okay. All right, so how do we know it's decreasing, by the way? Well, as n gets bigger, this guy gets smaller, right? All right, so now we take the limit as n goes to infinity of this guy. That's 0, okay? So the original series converges by the alternating series test. Okay, we're moving along. We have this one, summation n goes from 1 to infinity, n squared e to minus n cubed. So here I can see an obvious substitution. Hopefully you can too, so a good candidate is the integral test. So again, I wrote it as a function instead. F is this guy. We know it's always positive for all real x actually, because x squared is always positive. The exponent is always positive, so it's positive. Okay, so that's easy. Now let's find f prime to show that this guy's decreasing. Here we need product rule and chain rule, so be careful. First, d second, derivative of e to minus x cubed would be e to minus x cubed times derivative of minus x cubed, which is minus 3x squared, right? Plus second, d first derivative of x squared is 2x. Okay, so I can factor out the e to the minus x cubed, so that's what I did. Here I can combine these two to minus 3x to the fourth, and we're still left with 2x there, okay? We know this is less than 0 for x greater than or equal to 1. All right, so how did I get that? Well, e is always positive. When we start from x is 1, because I want to start there since n is starting from 1, that's a good place to start. If not, we can always shift upward if we need. But already at 1, I can see that when x is 1, this term would be negative. Okay? And then as x gets bigger, clearly this guy would dominate, so I'll make the term negative. So we know that it's negative for x is greater than or equal to 1. So the sequence is positive and decreasing. Okay, so we did our job there. Now we can use the integral test, integral from 1 to infinity. This is the x squared, e to minus x cubed dx. So I let u be minus x cubed. du is minus 3x squared dx. So we make the substitution. We get negative 1/3 integral from negative 1 to negative infinity e to u du. Okay, so let me quickly go over that. This is e to u. That should be clear. X squared dx, that is du over negative 3. So du divided by negative 3 is over here. And then limits of integration. When x is 1, u is negative 1. When x approaches infinity, u approaches negative infinity. Okay, so I flipped the limits and got rid of this negative sign to make it look a little nicer. Though I didn't have to, okay? So here we can easily find the integral of e, that's just e. We evaluate from negative infinity to negative 1. So we get 1/3 e to negative 1 minus 0, which is 1 over 3e. This is convergent, so this guy must converge also by the integral test. All right. How many more problems do we have? Okay, this is the last one. Okay. We have this series. Summation n goes from 1 to infinity. n over n plus 1 to the n squared power. So this one, the whole series is to the n power. It's actually n squared power, so let's use the root test. So that's the limit as n goes to infinity to nth root of this guy. When we took the nth root, well, this is n squared, so we still have an n there. All right, so this is our limit now after the nth root. So this, you have to be able to recognize that this looks very close to e, the limit definition of e. I can factor out n or divide this whole thing by n. Oh, actually, I can't say that. Excuse me. I could factor out n on top and n on bottom, and the n's would cancel. So when I do that, it'll be 1 over 1 plus 1 over n to the n. And this might be the more recognizable form of e. So I don't know if they teach this in Math 2A anymore, honestly, but this is the limit definition of e. All right, this is greater than 1. So remember what the root test says? If it's greater than 1, the series diverges. Okay, let me double check that this is the last problem, because I don't recall this being the last problem. But let me see. Oh, it is. Okay. Then that's it. Hopefully this video was helpful. Hopefully you just seeing me tackle the problems and going down this list, and me just talking out loud, saying what my thought process is, was helpful for deciding which test to use. All right, and then hopefully the calculations and all that were helpful too. The main part was to show you how I thought of which test to use, and then clearly I have to also show that the test works. That's why I solved all the problems too. All right, so please give this video a like if you found it helpful. Please subscribe also if you haven't already, and please share this video if you have friends that are also taking the course that are stuck on this and you found this to be helpful. Please share this to your friends also. All right, thanks, and I'll see you in the next video.